Space is quiet. It does not speak. It does not echo with thunder or wind. It does not leave ash or dust behind after it storms. And yet, it remembers. Beneath its silence, the universe is constantly at work, expanding, evolving, trembling under its own weight. Black holes collide, stars implode, galaxies stretch and shear, and through each event, the very structure of reality trembles and changes. Sometimes, those changes are not undone. What if the cosmos carried a kind of memory, not in molecules or matter, but in the invisible warp and weft of space-time itself? What if every massive collision, every twist of gravity, left a permanent trace, etched not in stone or steel, but in the subtle curves of the universe? This isn't just poetic speculation. It's real, it's measurable, and it has a name. Gravitational memory, a physical memory written into the geometry of existence. Tonight, we'll explore one of the most profound ideas in modern physics, that space doesn't just stretch or ripple, it remembers, and that the universe, in all its vast complexity, keeps the past within it. Gravitational waves are not like any wave we know. They are not made of particles. They do not ride air or water. Instead, they are ripples in the fabric of space-time itself, a single, unified entity where the dimensions of space and time are inseparably linked. When two massive objects, black holes, neutron stars, even collapsing stars, spiral around each other, they disturb this fabric. Their motion sends out gravitational waves that ripple outward in all directions, moving at the speed of light. For decades, these waves were only a prediction, an elegant mathematical artifact buried in Einstein's equations. They were too subtle, too soft to detect, until 2015, when the LIGO Observatory finally heard them for the first time. It was a chirp, a fraction of a second long. Two black holes, billions of light years away, had collided. Their death spiral had rung the fabric of space-time like a bell, and Earth had shivered in response. Our planet had moved, infinitesimally, yes, but undeniably. Einstein was right. Gravitational waves were real. But what happened next? That part of the story, the part almost no one noticed at first, that was where the memory began. When a gravitational wave passes through space, it stretches and compresses the distances between objects, like a jelly being squished in invisible hands. This distortion is temporary, or at least we once thought it was. But a deeper analysis reveals something unexpected. After the wave is gone, something remains. Not motion, not vibration, but a shift, a tiny, permanent displacement. Objects that were once a certain distance apart are now, ever so slightly, farther or closer than before. This is gravitational memory, the idea that space-time does not bounce back perfectly after a wave. Instead, it retains a residual imprint. The fabric is forever altered. It's as if the universe takes a breath and never fully exhales. The effect is so slight that it's undetectable in daily life. But over cosmic timescales, across billions of galaxies and countless collisions, these memory imprints accumulate, layering, warping, slowly reshaping the contours of the universe itself. In this way, gravitational memory is the universe's archive, a whisper of every catastrophic event etched into its bones. So how does the universe keep this record? Gravitational memory emerges from the deep laws of general relativity. There are two types, linear memory and nonlinear memory. Linear memory arises when the masses involved in an event, like black holes or neutron stars, undergo a change in momentum. If a system of objects moves in a certain direction and then suddenly changes, like two stars merging into one. The shift in momentum creates a lasting deformation in the surrounding space-time. Nonlinear memory, on the other hand, is more subtle and mind-bending. It arises not from matter, but from the gravitational waves themselves. These waves, carrying energy as they travel, also carry momentum. When they leave a system, they carry away not just motion, but curvature. The waves themselves distort space, and that distortion never fully returns to zero. It's like a ripple that doesn't vanish, a wave that doesn't fade into stillness, but leaves behind a permanent shape. In both cases, memory is not a metaphor. It is a quantifiable change in the geometry of the universe, and it means that space literally remembers. The implications of gravitational memory reach deep into one of the most puzzling debates in physics, the black hole information paradox. According to quantum mechanics, information can't be destroyed. Yet black holes, by their very nature, seem to erase the identity of everything they consume. They collapse into singularities, cloaked behind event horizons from which nothing, not even light, can escape. So where does the information go? Some theorists believe gravitational memory may be part of the answer. If every collapse, every merger, every explosion leaves a permanent, physical change in space-time, then perhaps the information isn't lost at all. Perhaps it's not encoded in matter or light, but in geometry, the shifting of space, the gentle repositioning of particles, the subtle curvature that remains after a wave passes. These might be the universe's way of keeping a ledger. Gravitational memory might be more than just a ripple. It might be a record, a correction, a preservation of cosmic truth. Today's detectors, LIGO, Virgo, Cagra, have changed physics forever, but they are only the beginning. To truly measure gravitational memory directly, we need to reach farther. Wait longer. Listen more closely. That's where missions like LISA, the Laser Interferometer Space Antenna, come in. Scheduled for launch in the 2030s, LISA will place a constellation of spacecraft in orbit around the Sun, millions of kilometers apart. From that vantage point, it will be able to detect lower frequency waves, signals from the most massive events in the cosmos, supermassive black hole collisions, galaxy mergers, even the whisper of the early universe. And perhaps, with enough time and sensitivity, we'll see not just the wave, but the memory it leaves behind. When we do, we'll be reading the universe's most intimate notes. We'll be unlocking its historical record, not written in atoms, but in curvature, not written in sound, but in silence. The universe is not static. It flows. It bends. It forgets nothing. Every time two black holes collide, every time a star dies in a burst of light, every time space-time is disturbed by violence and rebirth, the memory remains, not in human minds, not in fossils or ruins, but in space itself, in the stretch of distance between objects, in the tilt of an orbit, in the silent, permanent shift of space-time. Gravitational memory tells us that time doesn't just pass. It accumulates. It doesn't erase. It engraves. We are living in a universe made of stories. Every square inch of space carries the echoes of creation. And somewhere, written in geometry itself, is a record of everything that has ever been. The universe doesn't speak, but it remembers.